This lesson is on optimization. It's a lot of finding the maximum or the minimum in word problems. I'm going to use the notes that have already been filled in, and you have a copy of them as well, so we're just going to talk through it. Number one, a manufacturing company has determined that the cost of producing an item can be determined from that equation, which is quadratic, where X is the number of units that the company makes. How many units should the company manufacture in order to minimize the cost? And I know that's a lot to take in, but the first thing I want to point out is, what is it asking? How many units should the company manufacture? It's not asking what the minimum cost is. It's just asking how many units you should produce in order to minimize the cost. So when you finish with these problems, always go back and make sure that you have answered the question that they asked, not the question that you think they should have asked. Okay, so I need to find the derivative, and here's why. If this is a parabola that opens up, it's going to have a minimum. My job is to find that minimum, so I'm going to take the derivative. I'm going to set it equal to 0, and I'm going to solve it. And that's going to give me my critical value. Sometimes you'll have curves, and you're looking for that. To figure out if it's a max or a min, you're going to do the second derivative test to see if this critical value makes the second derivative positive or negative. If the second derivative is positive, you know it's concave up, which means you're going to have a minimum. If it's negative, it means it's concave down, which means you're going to have a maximum. So all of that is going to be used in these kinds of problems. Okay, so the first thing I did was I found the derivative, and I've gone back to the, instead of c prime, the dc over dx. It is dx because my variable is an x. I have no idea why they have changed back to this, but I'm just sort of following their lead. So the derivative of c, the first derivative, super easy. Set it equal to 0, add your 176 over and divide by 16, so I get 11. 11 is my critical value. To figure out if it's a max or a min, guys, we know that this is a parabola. We know it opens up, so we know that this is going to be a min. But if this is a free response question, you have to show mathematically that you know that it's a min. So you're going to use the second derivative test to check. So I take the second derivative of this, which I take the derivative of my derivative. So again, that's d squared c over dx squared. And that just gives me a positive 16, which means that the second derivative is always positive, so it's always concave up, making my critical value a minimum, because if it's concave up, then that's going to be a minimum. And then if I go back and read, it should make sense. How many units should the company manufacture in order to minimize the cost? So the company should manufacture 11 units in order to minimize the cost. If they had said what would the cost need to be at 11 units, to find the minimum cost, you need to find f of 11. Again, that's the original function, not the derivative. So the minimum cost is $832 at 11 units. From what I have read, they're very big on making sure you have units of measurement, especially on your word problems. So that's why I have 11 units. And if they were to ask this, $832. Number 2, a rocket is fired into the air and its height in meters at any given time can be calculated using that formula. Find the maximum height of the rocket and the time at which it occurs. So this wants both. So I take my original function and I'm finding the derivative, so the constant goes away. Find the derivative, set it equal to 0, add the 9.8t over, divide by 9.8, and get t equals 20. That is my critical value. I have to do the second derivative test to see if it's a max or a min, so I'm taking the second derivative, and that's just going to give me a negative 9.8. It is always negative, so I know this is always concave down, so I know that at t equals 20, that is a maximum. So what I know right now is my vertex. I know that my x value or my t value is 20, but I don't know this value yet. So I find h of 20, and again, it's the original function, and I get 3,560. So when you're talking height, this is x, this is y. So it makes sense that he's height, this is time. So as time goes across, tells you what the height of the rocket's going to be. So at 20 seconds, the max height is 3,560. The max height, it happens at 20 seconds. Again, a sentence labeled all nice and pretty. Okay, so now I have a box. Max wants to make a box with no lid from a rectangular sheet of cardboard that's 18 by 24 inches. Okay, so here's my rectangular sheet of cardboard, and it's 18 by 24 inches. What he's going to do is he's going to cut a square out of each corner, and each of the cuts are size X. So all of these are X's. Okay, and then what he's going to do is he's going to disregard those. He's going to throw those away. So those are gone. And then what he's going to do is he's going to fold on the dotted line, and this piece right here becomes the tall flap of one of the sides of the box, like a shirt box. And this flap right here is going to fold up and become this guy. So you have to think about your new measurements of your box. Okay, so if the sheet was 24 by 18, then this right here is going to be 24 minus 2x, because you're taking 2 of these out. Then this distance here is going to be 18, the whole thing, minus 2 of those x's. So 18 minus 2x. And then the height of your box is going to be x, because you're taking this flap and turning it up. Now I want to maximize the volume. You need to think about your related rates problems. Find words that tell you which formulas to use. It wants the volume. Well, the volume of a box is length times width times height. Now, I don't get super carried away with whose length and width and height. I just always put the little guy in the front, and then those two, and then you very careful lobster, combine your like terms, distribute your x through. And all of that I have labeled with all just straight up V's. So I know that I have not taken the derivative yet, and I think we need to make sure that we're really careful about labeling it so we understand what we have. Again, remember, we're trying to focus on the big picture. All right, the question says, find the value of x that maximizes the volume. So this is my formula I want to max. So I'm going to take the derivative of it, and he's cubic, right? So he does something like this. And I want to maximize the volume. So I need to find that hump right there. So that's why I take the derivative. So that, pull the 2 down, knock the power, pull the 3 down, and knock the power down by 1. Set him equal to 0. To make life easier, I tried the GCF of 12. They're even. I know I can take a 2 out. I tried GCF of 12, and it worked. So I have this, but it doesn't factor. But it is a very nice complete the square. If it wasn't, I would have done the quadratic formula. If it factored, I would have factored it. So I subtracted my 36 over, added 49 to both sides, got this, square rooted both sides, and then added my 7 over. Then I'm going to get my decimals for those. So the first one is 10.6. That's the 7 plus. Then the 7 minus is 3.4. One of these answers doesn't make sense. Okay, think about what x represents. X is the little corner that we're cutting out. So one is 10 and some change, and one is 3 and some change. Go back and look at your box. If this, keep drawing my picture. If this distance is only 18 to begin with, you can't cut 10 from each corner, because that would be 20, and you only have 18 to start with. So cutting 10 inches from each side is not, you're not able to do that. So if the box is only 18 inches wide, you can't cut 10.6 inches out of each corner. So he is not logical. So I'm going with the 3.4 for my critical value. So now I'm going to do the second derivative of this guy. And I got this. Now, this is not always positive or always negative. It depends. Well, I only care what is it at 3.4. So at 3.4, I plug a 3.4 in here, and I don't really care what the number is, but I care that it's negative. So at this number, we are concave down. So therefore, 3.14 is a max, which, if you go back to the original problem, I want something that maximizes. So I have just proven that I have found the top of that hump. And all of this you have to show. So if x is 3.4, let's see, and I did length, width, height. So 3.4 is there. And then to get the length and the width, let's see, one of them was 18 and one of them was 24. Okay, but it's not just 18 minus one of the corners. Remember, it's 18 minus 2x and 24 minus 2x. So that's where these two numbers came from. So length by width by height. Okay, a rectangle is to be inscribed in a semicircle with radius 4, with one side on the semicircle's diameter. What is the largest area this rectangle can have? Okay, that's a lot, so let's stop. A rectangle is to be inscribed in a semicircle with radius 4. Okay, let's look at my drawing. So I came over here, said, okay, semicircle, radius 4. 1, 2, 3, 4. 1, 2, 3, 4. 2, 3, 4. Okay, you need to know the equation of a circle, which we did in pre-calc. X squared plus y squared equals r squared. I'm on the origin, so I don't have to worry about my center being off the origin. So I've got x squared plus y squared equals 16, because again, it's r squared, so it's 16. Okay, then I took that and I solved him for y. Okay, now hold on to that. I'll explain why here in just a second. Inside this semicircle, I have a rectangle. Okay, and it says with one side on the semicircle's diameter. Well, here's the diameter. And one side of my rectangle is on the diameter. What is the largest area the rectangle can have? So guys, I want to maximize the area of my rectangle. So that is where I started. So again, don't just sort of go flailing around with some formulas. Read it, see which formula you need, and that's the one you're going to differentiate. And the problem with this is I have two variables in here, and I need to get it all in terms of one variable. Okay, so let's look at this rectangle. Let's look at the one I've drawn up here in pencil. Length and width. Well, this is my length, and this is my width. Well, this distance is going to be some x. I don't know what it is, but it's on the x-axis, and so it's going to be an x. So the length of this rectangle is going to be 2 of those, because he's centered on the origin. So 2x. The height of this rectangle will go until it hits the edge of the semicircle. So that y value is going to be this y value because they meet. So that's why I solved this thing for y, because now I've got my 2x in for here, and I'm going to put this in for my width. And now I have an area formula that's completely in terms of x's. I rewrote it like this because I know I'm about to differentiate it. I went dA over dx, derivative of the first guy, leave the second guy alone, plus leave the first guy alone, derivative of the second guy, and it's a chain rule. Be careful there. Then let's see, left him alone, cleaned up all my littles. So x negative 2x squared, so there's him. And then there's this guy, and then I took the 16 minus x squared to the negative 1/2 out. Going to leave me with a 2, and remember when you do this minus that, you're left with a 1. And then he's completely gone because we took him out, so left with a negative 2x. I distributed here and then combined my like terms with this guy and ended up with that. Then I popped this to the bottom. Okay, so here I am. This is my first derivative. So then I set it equal to 0. Well, the bottom's going to fall away. I subtracted my 32 over. I divided by -4, and then I rooted both sides. Well, x equals plus or minus root 8. Well, the positive root 8 is going to be this distance, and the negative root 8 is going to be this distance. So I'm just going to deal with the positive one. So x is a positive root 8. So now I'm going to take my positive root 8. Again, this one, I left the negative root 8 in here, and when you plug it in to get the area, it gives you a negative number. So again, that just shows you that you shouldn't use your negative. All right, now let's talk about why I have the -4 and the 4. The domain of my original function of the semicircle is from -4 to 4. Let's go back and let's look. What would happen if x was bigger than a 4? Well, that would be 16 minus something bigger than a 16. So that would make my root a negative, or it would make me root a negative number, which I can't do. And if, so I can't go outside of a 4. If I go outside of a -4 and I square it, that number is going to be bigger than a 16. And again, that would make me have a negative root. So this is my interval. So I'm going to use them as my critical points. Well, when I plug in -4 and a 4 into the original function, I get a 0. I get no area. Again, these are my x's. That's the length of the rectangle, or half of it. And then this is my area, because again, I'm plugging it into the area formula. I'm going to show the plugging in the positive root 8. So here's my area formula. So 2 times root 8, and then the square root of 16 minus the square root of 8 squared. Well, the square root of 8 squared is just an 8. And then 16 minus 8 is an 8. So I have root 8. So I have 2 root 8 times root 8. Well, root of cow times root of cow is a cow. And then 2 times 8 is 16. So that's where that area came from. Just watch the nitty-gritty math. So this, which looks like I have, there we go. This becomes my max because he is my biggest number. Again, the endpoints of my domain didn't work because they gave me 0 as an area. Plug them in and you'll see. You get a 0. This one gave me a negative area. We talked about how it couldn't be negative, and that just proves that point. Area can't be negative. So this is the x value it needs to be. This is the max area. Okay, now let's go back and let's read the question. What is the largest area this rectangle can have? So my answer is not root 8. My answer is 16 units squared. It happens when x is root 8. Now something else this question could say is, what are the dimensions of the rectangle? Well, x is root 8. Let's go back up here and look. If x is root 8, what would the dimensions of your rectangle be? Well, if that's root 8, then what's this length? It'd be 2 root 8. Okay, how would you find the height? Well, again, that's my y value. So I would plug in a root 8. And I get root 8. So I would be 2 root 8 by root 8. Those are the dimensions of my rectangle. So again, lots of different questions they could ask here. They could ask for the area, which they did. They could ask for the dimensions of your rectangle, and they could say what x would cause you to have the largest area. A rectangular field bounded on one side by a building is to be fenced in on the other 3 sides. 3,000 feet of fence is to be used. Find the dimensions of the largest field that can be fenced in. Okay, well, here's my awesome drawing. Here's your building, so he doesn't need a fence. I need fence here, here, and here. In no way, shape, or form does it tell me that it has to be a square. So all I know is that this and this are the same, because it does say that it has to be rectangular. So these guys, I'm going to let them be x, and I'm going to let him be a y. They could all be the same. I don't know. Okay, so I have 3,000 feet of fence. Well, that's not area. I don't put fence all through my field. That's perimeter, but I only want fence where I'm green. So 2x plus y equals 3,000. Okay, now just hold on to him for just a second. What are we trying to maximize? The dimensions of the largest field that can be fenced in. So I want to maximize the area of the field. Well, area of this field is length times width, which is x times y. So this is the formula I need to take the derivative of, not perimeter, area, because I'm trying to find the dimensions of the largest field. Well, I can't take the derivative when I have two different variables if I'm trying to solve for one of the variables. I don't want to do implicit differentiation. So what I'm going to do is I'm going to take this sort of side equation and I'm going to go solve him for y, and then I'm going to substitute this in for y. So this x stays put, and in place of the y goes what y equals from the other equation. And then I distribute my x. That's my area formula, and then I take the derivative. Then I come over here and set it equal to 0, add the 4x over, divide by 4, I get 750. That's my critical value. I have to take the second derivative to see if it's a max or a min. Let's see, what am I looking for? Largest. So I'm looking for it to be a max, but I have to prove it. So I take the derivative of that, so that's d squared a over dx squared. And that derivative would be a -4, which means no matter what I am, and I'm a 750, but no matter what I am, this thing is always negative. So it's always concave down, so I have just proven that 750 is a max. So I've got the field should be 750 by 1500. Okay, well, let's see where I got the 1500. Well, remember this formula up here that found y? Y equals 3,000 minus 2x. Well, that's this, and I know that x is 750, so I'll plug the 750 in for my x, and that's where the 1500 came from. Then the actual area is literally length times width, and I got 1,000,000 and some change feet squared. And I don't have measurements on here. 750 feet by 1,500 feet. Now, let's go back and read the question. What did specifically it ask for? Find the dimensions of the largest field. So it really just wants this. This is extra information. Number 6. A poster is to contain 100 square inches of a picture, surrounded by a 4-inch margin at the top and the bottom, and a 2-inch margin on each side. Find the overall dimensions that will minimize the total area of the poster. Okay, so here's my beautiful drawing. Here's the picture, and I let it be x and y. I've got a 4-inch margin on top, either side, and 2 inches on the bottom. So the area of the whole poster, this is going to be x plus 4 and 4. So he's going to be x plus 8. And this is going to be y plus the 2 and the 2, so y plus 4. So that's the dimensions of the whole poster. So I've got my x plus 8, my y plus 4, and I multiply them out. Now be careful, this is not x plus 8 times x plus 4. So x times y, xy. 4x, 8y, 32. None of them are like terms. I can't combine any of them together. So here I am, and I'm still carrying my a to make sure that I know when I've taken the derivative. I can't take the derivative. I don't want to take the derivative when I have two different variables in here. I don't want implicit differentiation. Okay, it gave me another piece of information. It's 100 square inches of a picture. Well, my picture is represented by x times y. So that area should equal 100, length times width. Then I can take that formula, solve it for y, and use that to replace all of my y's. Now my area formula is completely in terms of x. Well, let's clean it up a little bit. Those cancel. So plain old 100 of 4x. That's going to give me 800 over x. I know I'm getting ready to take the derivative, so let me pop him up with a negative power, and then plus my 32. And then I've got like terms here and here, so just a little cleaning up. So this is my platform area equation. So now I'm going to take the derivative of that. So that gives me 400 minus 800 x to the negative 2. I'm going to rewrite it. Pop that x to the negative 2 down to the bottom. Set it equal to 0. Add the 800 over x squared over to the other side. And then when I get here, I'm going to cross multiply. So 4 times x squared gives me 4x squared. 800 times 1 gives me 800. Divide by 4. Square root both sides. I went ahead and popped the 10 out. I know you don't have to, but I did. Can't be negative because we're talking about the length of something or the width. It's a measurement, so it can't be negative. So I know that I'm looking at 10 root 2. Now I need to prove that this is a, what are we trying to do, max? No, we're trying to minimize the area. So I need to prove that this is a min. Okay, so I'm going to take the second derivative of this guy. Okay, well the 4 is going to go away. Negative 800 times negative 2 is a positive 1600. Then take one more off the power, so x to the negative third. Okay, so this is my derivative. It's not always positive or always negative. Okay, I've got to see where it is at 10 root 2. So I plug my 10 root 2 in and do some math, and I find out that it's all positive. I don't care what number it is, but I find out that this at 10 root 2, I'm going to get a positive answer. So I know it's concave up. So I know that at 10 root 2, we are a minimum. So I've just proved that it's a minimum. My x is 10 root 2. I need to go find my y. Well, I'm going to use this formula from way back at the top. Y equals 100 over x. Then I'm going to plug my 10 root 2 into the bottom. I'm going to clean these up. And that's my y. Okay, now let's go back and let's read the question. Find the overall dimensions that will minimize the total area of the poster. The overall, not the dimensions of the picture, the dimensions of the poster. Well, the poster is x plus 8 and a y plus 4. So here's my x plus 8 and here's my y plus 4. My x is 10 root 2, so I'm 10 root 2 plus 8. There's my y, and I got to add 4 to it. So my dimensions are 10 root 2 plus 8 by 10 over root 2 plus 4. Number 7. An open top box with a square bottom. That's important. Square bottom and rectangular sides is to have a volume of 256 cubic inches. Find the dimensions that require the minimum amount of material. I'm not trying to minimize my volume. I'm trying to minimize the amount of cardboard it takes to make this box. So I'm trying to minimize the surface area. Okay, now remember this box has no top on it. Well, it's a square bottom. So that's x times x. So there's the bottom right there. Now my 4 sides are x times y, and there are 4 of them. Okay, so 4 x times y. So again, this is not volume, this is surface area. So I have the amount of material it takes to make the bottom, and then I have 4 sides. Okay, so then it gave me other information. It said 256 for my volume. Well, volume is length times width times height. Well, that's x times y. So that's x squared y. And it told me that the volume is 256. So I can put a 256 in for my v. So now I'm here. I can use that equation to solve for y. Then take this and plug it into this equation wherever I have a y. What that does is that gives me a surface area formula that's completely in terms of x's. I've got a little cleaning up to do. 4 times 256 is 1024. A pair of the x's cancel. It leaves me with an x on the bottom. And then I know I'm about to differentiate, so I'll pull him up to the top with a negative 1 power. That's my surface area formula. Then take the first derivative. Power rule, super easy. Then I'm going to take this, I bump this guy down to the bottom, then I add him over, then I cross multiply, so 2x cubed equals 1024, divide by 2, cube root both sides, no positive or negative when you cube root, so x equals 8 is a critical value. But I have to prove that, what are we doing, max or min? Minimum amount of material, that this is minimum. So I do the second derivative of my first derivative. Nice, easy power rule, so 2. Pull the negative 2 down front, multiply, and then take 1 off my power. Okay, so that's my second derivative. So now I need to see is that derivative positive or negative at 8. That's going to tell me if I'm concave up or concave down. So I plug an 8 into my x and clean it up. I got a 6. I don't really care that it's a 6. I care that it's positive. So I know I'm concave up. So I know that at 8, it's a minimum. Concave up at 8, so 8 is at a minimum. Okay, let's go back and read the question. Find the dimensions. Well, I have x, I need y. Well, remember, I have this formula that helps find me y. So I take this formula, I plug my 8 into my x squared, and I get my y value. So 8 and 4, so the dimensions of the box, remember it's length times width times height. So 8 by 8 by 4. Okay, last one. Find the point on the curve y equals the square root of x that is a minimum distance from the point 4, 0. Okay, so you should already see the word distance. You know we're going to be using the distance formula. Find the point on the curve. Okay, so that's your shooting star. So I come over here and drew him. I've got my point 4, 0. I want a point on here where it has the smallest distance to this point right here. So I'm going to let him be xy, and he's 4, 0, and I need the distance between those two. Okay, well, distance formula is x minus x squared plus y minus y squared, all under the square root. And I'm using these 2 points. Okay, I'm going to clean this up and just make it y squared. So this is my distance formula. The problem is I have an x and a y in them. And that's not good. So I'm going to take this equation that it gave me, and I'm going to use it to substitute this in for the y. So it becomes this. Then when you square or square root, the x is going to fall out. I write this twice in lobster, and then I've got like terms here and here. So that gives me this. I know I'm about to differentiate, so I'll go ahead and write it with a power. Okay, so this is my distance formula. Then I'm going to come up here and I'm going to go dd over dx. So I'm going to use the chain rule. So pop the power out front, take 1 off my power, and the derivative of the inside. Okay. Then I'm going to leave this guy on top, and then I'm going to and I'm going to move that to the bottom. Okay, so that's my first derivative. To set it equal to 0, the bottom's going to go away. Solve it, I get 7 over 2. That's my critical value. This is the only hairy part of all of these problems. All of these 8 problems is this one right here. The second derivative of this one is hideous, but you've got to be able to muddle through it. Okay, so I'm taking this, and I'm going second derivative. Okay, low, d high, minus high. Then when I pull for the derivative of the low, when I pull the 1/2 out front, that's why I have a 1 there. Take 1 off my power, and then I just ran out of room. This guy should be sitting right there. And then the derivative of the inside. Over low, low. So that's my bottom squared. Okay. Multiply my littles. Leave this guy alone. Let's see. He's a 1. He didn't really count. Then I have this and this are my littles. So I have him squared over this guy, and then square the bottom. That's going to give me a 4, and they're going to cancel. So I have this. Okay. Then I'm going to GCF to the negative 1/2 out. So this and this, and I'm taking the negative 1/2 out. Gonna leave me with the 4. And let's see, remember when you do 1/2 minus a negative 1/2, it gives you 1, so I have 1 of those left. But then when you take the negative 1/2 out, it takes all of him out, and I'm left with that. Over, I'm leaving this alone, and I'm not going to distribute because I'm about to move him down. Okay, I'm going to distribute my 4 here. That's what all of that is. And then I'm going to write him twice. Now, I'd be real careful with this one. You have to write him twice in lobster and then run the shark through. So that's what gave me that. These canceled, and I'm left with a positive 64 and a negative 49. So that's where the 15 came from on top. I moved this negative 1/2 down to the bottom with that 1, and 1 plus the 1/2 gives me the 3/2. So this is my second derivative. Well, I need to know what is he at 7/2. Well, the top's going to be positive no matter what. Then I took my calculator and I plugged 7/2 into this with the 4 into the negative 3 or to the 3/2, and I got a positive. So I know that it's positive over positive, so we're going to be concave up. So 7/2 is at a minimum. Okay, so then I come over here. Let's go back and read the question. Find the point. Okay, well that's an x and a y. I have my x. I have my 7/2. I need my y. Well, I'm going to use this formula. Y equals the square root of x. So y equals the square root of 7/2. So that's where he came from. So that is the point that minimizes the distance between the shooting star and the point 40. Okay, it's not tons of new material, and it doesn't get super dicey, but you need to really make sure that you focus on which formulas you should use. And like if you'll notice in this one and almost over half of them, there's a primary formula that you're going to differentiate, and then there's sort of a side formula that you're going to plug in somewhere. Make sure that you are super clear on which formula you're going to take the derivative of. Whatever you want to minimize or maximize, that's the formula you want to take the derivative of.